Hello, everyone, and welcome. My name is Garaudy Etienne, and I'm a product manager here at MongoDB. Today, Evin and I will be demonstrating some of the exciting new distributed system features in MongoDB 4.4. Our first demo is Hedge Reads and sharded clusters. In a sharded cluster, we typically have a client, a MongoS, and a few replica set shards. The client sends a query to the MongoS, which in turn routes the request to the appropriate node in each shard. In this demonstration, we'll be looking at a sharded cluster where each shard has 5 members, a primary and 4 secondaries. When a user selects read preference nearest, they're indicating that they want the lowest latency available. But sometimes, queries can hit the nearest node and it might be busy. That node could, for example, be experiencing intermittent network or disk failures. This leads to a few random high latency results. One way of mitigating for those busy nodes is to hedge your read to an additional node. When your application makes a read, the MongoS automatically hedges the read to the 2 nearest nodes measured by network latency. We take the result from whichever node can produce it the fastest and cancel the read request from the other node. Your users get better and more predictable performance because we've eliminated the long-tail query latency outliers. Next up is mirrored reads for cache warming. Most of our users' applications read from the primary, and for the majority of times, that's never an issue. But what happens when a primary node becomes unavailable? An election is triggered, and within seconds, we elect one of the secondaries as the new primary. We then start directing reads to that new primary node. That new primary might not have the latest data in memory. Instead, data has to be read from disk. As a result, users can experience higher latency in the minutes after the election. We can avoid the high latency issue by mirroring our reads to the secondaries, slowly warming them in preparation for an election. With mirrored reads, if our primary goes offline, the caches of the secondaries have already been warmed with the most recently accessed data. This allows the cluster to quickly restore steady-state application performance. By default, 1% of all reads are mirrored. You can increase the mirroring percentage, recognizing that this will increase load on the replica set, or you can turn off mirrored reads entirely. And now, I'll pass it off to Evin, who will be demoing refinable shard keys and compound hash shard keys.
Thanks, Garaudy. My name is Evin Roesle, and I am also a product manager on the server team here at MongoDB. And now I'm going to lead you through a demo of refinable shard key and compound hash shard key. Okay, so let's get started. First, we will take a look at refinable shard key. Here is a simple document in a sharded orders collection where a user is collecting information about orders. It has a couple of fields, as you can see: customer ID, order ID, name, country, and zip code. For our example, we will be focusing on the first 2 fields, customer ID and order ID. Here is a visual of the sharded cluster. The orders collection is currently sharded on the customer ID, which you can see in the top right. Recently, the user of this sharded cluster is noticing that the sharded cluster is not performing as they expected. If we look closer at the shard's individual loads, we see that shard A has a much higher load than shard B and shard C. Now, why isn't this more balanced? With sharding, we normally expect that the load should be better balanced amongst the shards. Well, the shard key is used to control how data is distributed across the cluster. Get the shard key wrong and your data won't be evenly distributed, which is exactly what we're seeing here. If we look under the hood of each shard, we see that there are very large chunks of data on shard A. A chunk represents a subset of sharded data in a particular range. Each chunk has an inclusive lower and an exclusive upper range based on the shard key. Since this collection is sharded on customer ID, it appears that we have a lot of documents about 2 specific customers, which culminate into 2 big chunks, as you can see on shard A. Because the shard key only considers customer ID, the sharded cluster cannot split these chunks any further. If a chunk for a customer keeps growing, it eventually surpasses the threshold above which the system can balance the load amongst the shards via our balancer. Solving this issue used to be quite tedious, but with the introduction of refinable shard keys, all we need to do is refine the shard key to a shard key with a higher cardinality. So how do we do that? We can do this by adding order ID to the shard key, making the full key customer ID, order ID. Now that we have defined our shard key to customer ID and order ID, the jumbo chunks can then be split. Once they are split into chunk sizes that can be moved by the balancer, we can now rebalance those chunks across all the shards more evenly. In the end, we should see more equal loads on each shard, as we see here. There are no limitations about when you can refine your shard key, and there is also no impact on your application's availability when you refine your shard key. It is a non-blocking and transparent operation. This means that you can start scaling out with a simple data distribution strategy and refine your shard key as your data grows. Or, if your data has evolved dramatically from where it started, you can refine your existing shard key to a shard key that is more applicable for your current data. Now let's take a look into compound hash shard key. Previously in MongoDB, you could have a hash shard key or a compound shard key, but not a combination of the two. We have now taken care of that with compound hash shard key. Again, let's assume we have a similar document in a sharded orders collection where the user is collecting information about orders. This time, however, we have an important distinction from our refined shard key example. Order ID in this document is a monotonically increasing field, which makes it more difficult to get an even distribution amongst our shards. When we were originally building our app, we thought that we would have millions of active users, all making roughly the same amount of orders. Because of this, we chose customer ID as our shard key. After a while, though, we found out that that was not what we saw in reality. We found that we actually have just a handful of extremely large customers instead that place the vast majority of our orders. Looking under the hood again, we can see that this could put us in the same situation where the majority of the data is on one shard, shard A in the example. Last time, we were able to refine our shard key and just add order ID, but remember, this is a little different. Order ID in this example is monotonically increasing, which will cause us to not get an even distribution in this sharded cluster by just adding order ID to the existing shard key. If we added order ID, this would split the data, but since the order ID is monotonically increasing, the data would still reside on the upper bound shard, shard A, and not be moved. With compound hash shard key, we can hash our order ID field, which then evenly distributes the data even though it is monotonically increasing. You have the flexibility to hash either the suffix or the prefix of a compound hash shard key depending on your application's needs. This provides more scalable and performant applications, all while reducing application and schema complexity. I hope these demos were helpful. Thank you all for joining both of us today, and please be sure to check out our other product booths to learn more about other new features.